Good morning. Today we're going to start looking at rates of change of real-world problems. So we have 3 of them on today's guided practice. You're going to need a ruler and a pencil and a calculator for today's lesson. So if you don't have those, get some kind of a straight edge that you can draw some of these secant lines that we're going to be drawing. Okay? So I hope you're back now with those 3 things. So here we are, average rate of change. For a linear function, we say the slope is the rate of change of the function. So slope and average rate of change are the same thing. Does the rate of change make sense if the function is not linear? So that's what we're going to focus on today. It would be really nice if real world problems were all nice straight lines, but you're going to see on our second and third problem that they're not a straight line. So here's a remote control car that moves in a line. The graph below shows the distance in feet from the remote of a remote control car from the person that's controlling it, t seconds after it's turned on. We'll look at each segment of the graph. Okay, so a couple things that's really important here. They told us that this is our distance in feet, and they said our time is in seconds. So I want to label these. Okay, now they say explain what the car was doing during the time interval corresponding with each line segment of the graph. And so down here in our table here where it says event, we're going to look at line A here first. So line A goes from there to there. And so here we're at 0 seconds, 0 feet. And by the end of the line segment A, we are at 15:15. So what does that mean? What way is the car moving? Again, the person's standing here, and then 15 seconds later, it's 15 feet away from them. So you have to kind of write small today. So maybe you can kind of write here, moving away. Okay, we're going to assume from the person that's controlling it. Okay, so now let's go back up here. Let's look at segment B, which goes from here to here. So at the beginning of 15 seconds, it's at 15 feet. And then over here at 35 seconds, it's still at 15 feet. So what's the car doing? I hope you said that it stopped would be correct. And then let's go look at C real quick. Letter C. Let's get a different color here. Is right here. So we started out at 15 feet, and then sometime later, now we're at 10 feet. So I hope you said moving towards the person. All right, finish the next ones here. Tell what D is doing. E, F, and G. Pause your video and then come on back when you're done. Okay, so I hope that you said here on D that the car is stopped again. E, the car is moving away from the person again. F should be stopped again. And then G, you have a special circumstance. Not only is it moving towards the person, but it moved all the way back to the person's feet. So whoever was controlling it, so it moved back to the starting position. So on that last one, make sure you said not only is it moving back, but it's moving all the way back to the person or to where it started. Okay? So now we're going to start filling in this graph here with some vital information that we need. So if we're looking at just time segment A, we want to know what was the beginning time, because this is my x-axis, time, and then this is my y-axis. So my beginning time is 0, and my distance is 0. So as a coordinate, that would be called 0, 0. Okay, now the ending time for segment A, it looks like it's 15 seconds later is where that dot is. So it's right here. My ending point is right here. Now we don't need a ruler here because it's just going to be a line on top of a line, but really we're doing a secant line, average rate of change between this dot here at the beginning and this one right here. So we have 15:15. So 15 seconds is 15 feet away. So that's my coordinate, 15, 15. Now, we got to write kind of tiny here. Let's find our velocity. So velocity is the same thing as slope. So we're going to take 15, take away 0 over 15 minus 0. We have 15 over 15, which equals 1 foot per second. So the car is moving at 1 foot every second. Makes sense. 15 feet, 15 seconds. All right, let's go to the next one. Now they said look at line segment B. So now we're looking at going from here to here. Now you said it was stopped, so it'd be kind of interesting to see what our slope is. You probably already know. So it looks like time started for B at 15 seconds, and the distance was 15 feet. So that's going to give me a coordinate of 15, 15. Then it ended at 35:15. So 35 seconds later, it was still at 15 feet. So my coordinate there is 35:15. So again, slope 15 minus 15 over 35 minus 15. We got 0 over 15, actually 20. So 0 divided by anything. A lot of people are saying 20, but it's really 0 feet per second. So that means the car stopped, just like we said in our event over there. All right, I'll do one more with you, and then I'm going to set you free to finish them up. Let's go to C. We want to know from here to here what was our average rate of change. Okay, now since it's a linear line, you could go down 2 over this many, and that would be the same thing, and then reduce it. But let's use our coordinates. We're at 35:15. So in 35 seconds at the beginning of C, we're at 15 feet. 35 seconds, 15 feet. Okay, and then our ending of the line segment C is 55:10, it looks like. Not 55:10, yep. Okay, so that's going to be called 55:10. So again, slope 10 minus 15 over 55 minus 35. So we have a minus 5 over 20. And I want it per second, so the best way to do that is I want to get down to 1, so I'd have to divide both by 20, or I just take the numerator divided by the denominator. So -5. Now it's a negative, but I'm not concerned because you can't have a negative speed. So I'm just going to ignore the negative sign, but I get a 0.25 per second. So he's going 1/4 of a foot per second. Make sure you put units. Okay, so not very fast. It's actually pretty slow. All right, so finish D, E, F, and G, and pause your video, and then come on back and let's see if we have the same thing. Okay, welcome back. I have my chart filled in, so I think we stopped up here at 0.25 per 1 second. So the next one, you should have had 0 feet per second. Well, that makes sense because on D, on the graph up there, he stopped, didn't go anywhere. And then I had a 0.6 feet per second, then a 0 feet per second. Again, he stopped if I look up there at F. And now on his way home, he was going 1.3 feet per second. So now as we look at our graph, if they said, well, what's his fastest speed? It looks to me like as we scan up and down, the coming home was the fastest. Okay. All right. So that's what we're doing today is we're looking at a graph. Now this is where you're going to need your ruler. So this girl was running errands for her mother. All the stores in her house are located along Straight Street. She starts from home. On the graph below, her distance from home is D, is shown, and her arrival at the store is marked as G. Oh, D is the grocery store. Oh, D is the home. So right here means she's at home. So then G is the grocery store. H is the hardware store when she got to the hardware store, and then her arrival at the auto parts store is the A. Time is in minutes, so that's important. And then her distance is in miles. That's important because it's going to be miles per minute, but most of the time when we're driving a car or something, we don't do it miles per minute, so we'll talk about that in a second. Okay, so what was her average velocity? So velocity is the same thing as speed, so to speak, between her home and the grocery store. So let's go draw our secant line. We want to go from the home to the grocery store. So what we're talking about is a line average rate of change from here. Now it's a curved line, so you'll see that we can't compensate for the whole curve. So we're going to draw a line from there and find, quote, the average. That is very important. We're finding the average. So it looks like she's starting now at 0, 0 would be my first coordinate. And then when she got to the grocery store, it was 15 minutes later, and it looks like it was 15 miles away. Let's find the slope. So it's 1 mile per minute. Well, usually when we do speed, it's not miles per minute. We want to know miles per hour. So how many, let's convert it over. How many minutes are in an hour? So it'd be 60. So we're going to multiply both of these by 60. So we're going to do that often because we want to know how many miles per hour. So she's really going 60, and you can abbreviate miles per hour. Okay. Would you feel safe as a passenger if you were in her car going to the grocery store at 60 miles per hour? Maybe, depending. If it's in right down the street here, I don't think I want to be going 60 miles per hour in a 35, 45 mile per hour zone. But like if the grocery store was up in Mesa and you're going down Ironwood, it might be 60 miles an hour. Okay, that would be safe. That's a safe highway. How long was she at the grocery store? Now, again, gonna have to pay good, close detail to this. So, where did she start at the grocery store? She started right here. And then when did she leave the grocery store? You can see that the line starts curving here. So, she must have gotten in her car and started driving away, or actually towards the hardware store. The hardware store must be closer to her house. Kind of like our remote control car. If it's going down, that's not her speed. That just means the distance is closer to her house. The hardware store is closer. So how many minutes was she at the hardware store? Yep, they're counting by 5, so I hope you said 20 minutes here. Okay. What was her average velocity between the arrival at the grocery store and her arrival at the hardware store? So let's get our ruler out again. Her arrival at the grocery store, not when she left, and her arrival at the hardware store. So we're going to look for her average rate of change. Now, she was at the hardware store for 20 minutes. So it's kind of interesting that we had factored that in there because that has nothing to do with her speed. Okay. She was there for a long time. 20 minutes, I think it was. So now let's do that. Looks like she's 15:15 when she got to the grocery store. And then when she got to the hardware store, looks like 55:10. Okay, so again, find slope. Even though it's going to be a negative slope, we're going to ignore the negative part. We just know she's coming back towards her house, is what that negative part is. Now, I get 1.125 miles per minute. But again, I don't want per minute, so I'm going to multiply them by 60. 1.5 miles per times 60 is 7.5 miles per hour. It's important that converting it to miles per hour. Okay. Pretty slow, but it's slow because they factored in that she was at the grocery store for 20 minutes. How long was she at the hardware store? Now be careful on this one because this one's really kind of easy to misinterpret. So here she is at the hardware store and she doesn't leave until right there because that's where I start to see the curve change. Okay, so we can't say she was at the hardware store for 5 minutes. So you might say something like 6 or 7 minutes. It's a little over 5. Okay. What was her average velocity from the time she left the hardware store to the time she arrived at the auto parts store? So this one, when you draw your secant line, you have to be very careful that you do it from when she left the hardware store to her arrival at the auto parts store. So it's going to be something like that. My A is off a little bit there. Okay. So let's call it, I don't know, what do you want to call it? Arrival. So 62 maybe? Let's call it 62. Unless she was there for 7 minutes. So 62. I think it was 10. She's 10 miles away from home. And then the auto parts store, she drove away from her home. It's at, looks like 80-20. All right. Go ahead and find the slope for that one. Oh, this was 62. I get 0.55 miles per minute, but again, I don't want per minute. When we do speed of an auto, we do it per hour. So I'm getting 33.3 miles per hour. Okay. Okay, let's find, and they want us to put a point P. Find a point P. So they want us to draw a P on Sherry's home and the grocery store, where her average velocity before that point was less than her average velocity of the entire trip to the grocery store. So this one's a little confusing. So they want us to look at the graph. They want us to put a P on the graph where her velocity was slower. So do you agree, like right in here's where she started going much faster? Right here's a pretty straight line. So let's put a point P right here. Okay, because before that, she's picking up speed here, it looks like. For the first 8 minutes or so, she's going faster and faster because she's going further distance or less distance per minute than right here. So let's see what they're going to ask us to do now. What was our average velocity between that point P and the grocery store? So let's go up there and draw our secant line for that one and get some numbers here. So we want to know how fast she was going from here to here. Okay, so let's call P, what do you want to call that? 10.6? Let's call it 10.6. Let's go find the grocery store again. It was 15.15. So let's find it. You see how the slope should go so fast here? 15 take away 6, 15 minus 10, that we're not even thinking about things. 15 take away 6 is 9 over 5. I want to divide that by 5 though, because I want, it's 1.8 miles per minute. But again, I don't want per minute, I want per hour, so I multiply that by 60. Dang howdy, if I did my math right, let me check those coordinates out. 10, 6. 10, 6. Yeah, it'd probably be okay. 10, 6. Looks like they're counting by 2.5s. So 6 would be okay. And my other coordinate was 15, 15. I like it. So make sure I 15 take away 6. Yeah. That's 9. And 15 take away 10 is 5. 9 divided by 5. I'm still getting 1.8 times 60. 108 miles per hour in that little segment there. So when you said, yeah, I'm comfortable, well, that last little bit there for her last, I don't know, 3 minutes, she's going like pretty dang fast. 108 miles per hour. So when you up there above said, I feel safe driving with her, if you said safe, you might want to rethink that. So again, it's when you have that curve there like that, that's why we find average. If she was going really slow there at the beginning. Draw line segment HA and compute its slope. So we're going to draw a line that says a line segment from H to A. So let's do that with our ruler. So now look, we're factoring in her time that she's at the hardware store as well. So this line slope should be less than when she left the hardware store because it's factoring in her time. So let's go with H is, looks like 55:10. And then A is 80:20. Find the slope. So now she's going 24 miles per hour. Let's see where it was when we did that other line. What color was that? It was the line green one. She was going 33 miles per hour when it's actually what she was doing. But when we factor in her time at the hardware store, she's going, so it's slower. What was she at? The hardware store or the grocery store? I can't remember. Hardware store. Okay. So what they're talking about here in Sherry's situation, her average velocity between the hardware store and the auto parts is the change in distance from the hardware store to the auto parts divided by change in time. So in other words, what they're getting at here, when we have a curved line like this, we can't, I mean, it is slow, but we have to draw our own line and we have to compensate for the curve. And so we're really trying to find an average. So we have to be really careful when we are factoring in a straight line, like at the hardware store where she isn't doing any movement from or closer to this, where her house is. So kind of that's very important in real life word problems. Okay. All right. So now let's do this rocket here below. Here's a toy rocket. T seconds after it was launched. So it looks like this is in seconds. And it's in feet is my elevation. So this rocket went up to 100 feet, it looks like. Label the points on the graph that corresponds to the rocket launch with O. So put an O there. And the highest point it reaches with an M. I don't know what happened to my... And then find the average rate of change of the height over time intervals given below. Okay, so we're going to do the same thing. So at time 0, which would be here, we have 0, 0. So that's an easy one. Now I'm not going to, I just want you to go with the coordinates, okay? And then time 2 is in 1 second. So in 1 second, that's right here. So we want a secant line that goes from there to there. We want to find the average rate of change. It's almost linear. Okay, so let's use those two real quick. I forgot 2. What was it? 1. Let's call that. What do you want to call that? 62. Okay, so 162. 62 take away 10s. 52. And that's 1. So, oh, actually, it's a 0 there, not 10. That's a 62. Can't read my own writing. My comma looks like a 1. So that's 62. So let's put our unit. 62 feet per second is how fast that rocket is flying. Okay. All right. You fill in the rest of this grid here. Pause your video and then come on back when you're all done. Okay, let's see how you did. I got all my answers here. First one, I got 62 feet per second. Then I got 32 feet per second. 10 feet per second, so it's kind of slowing down as it reaches the top. And then between 2.5 and 4, which if we look at that graph, 2.5 and 4, now we're coming back down. So we should have had a negative number there, but we're going to ignore it. We had 25 feet per second, then 0 feet per second, then 0 feet per second. So if I go between 1 and 4, you should have had a secant line between 1 second and 4 second, which makes sense. 1 second is right there at A, and C, or 4 seconds, is right there, and so we should have had a secant line going straight across. And now we had a 0 slope because, and this is extremely important, average rate of change means average. So we went up this much to get to M, and we went down that same much. So our change in our average rate of change is going to be a 0. They're at the same height. We went up just as fast as we came down. Okay. All right. Let's go and do some answering some questions now. What's the units for the average rate of change? In our problem here, what was our units? It was feet per second, right? Which time interval change were positive? So you need to write positive here. And so on our chart there, where did we have all positive numbers? Well, we had positives at 0 to 1. Here's where my negatives started, right here. So I have from 0 to 1, 1 to 2, 0 to 1, 1 to 2, 2 to 2.5 was positive. I think 2.5, was that where my M was? Yeah, it was. 2.3 was, no, 2.5. So where was it negative? It was negative from 2.5 to 4. And I think that was the only negative one I had, really, because I see my negative sign right there. This was 0 and this was 0, so that was it. Where was it 0? From 1 to 4. And I had another 0 of 2 to 3. Okay. Answered that one. Hey, I'm missing a question. Number 4. Number 4 seems to disappear. One of the most used rates of change is speed. What does the speedometer on your car measure? I'm hoping you're saying when you look at your speedometer in America, it's miles per hour. You're going to be getting your permit here pretty quick. Know that one. Okay? All right. So now here's your homework. This is a forensic case. On Wednesday around 8 p.m., this person reported that their daughter Sarah was missing as of 7 p.m. Wednesday, she had not checked into her beach house rental. They reported that she left the house at 7 p.m. Tuesday to go on a vacation. The police found her abandoned car with a GPS. A sketch of the graph from the GPS is below. Use information from the sketch to answer the following questions. Approximate to the nearest tenth as needed. So down here when they're saying hours, you need to be careful because this was 7, I can't remember, was it PM or AM that she left? 7 p.m. So you got to keep in track of this is 7 p.m. 8, 9, 10, 11, 12. This is midnight. 12 p.m. AM, I guess it should be. And then here's like 1 a.m. So this is now morning. So kind of keep track of that as you're going through here. So you can see that her GPS is not nice straight lines, curvy lines. And this is her miles from, so this is going to help them. What was her total distance traveled? All right, you answer all these. This is your homework. I just wanted to talk to you about this part down here. Make sure you convert these hours from the time she left is what that is. So you have to make sure you get the right units of time down there. Okay? All right. Not very many problems. You don't even have the whole chart to fill in. All right. We'll see you tomorrow. Tomorrow, you're going to need a ruler as well. We're going to do a little bit of parallel perpendicular lines, if I remember right. So make sure you have a ruler. We're going to review that before the 10th graders have the test. And it's also good for what's coming up on Pythagorean theorem and some of those things that we have to do coming up and preparing for next year. All right. We'll see you tomorrow.